All right, it's 7 o'clock. We're gonna get started with this class. Streaming is on, so I kind of like the streaming mechanism because I don't have to worry about saving the file at the end, uploading it, or deleting the file before I upload it. That sort of thing. It's like good. Well, so far I haven't found any problems with this approach yet. All right. So what we'll do today is to continue to talk about the homework assignment in case anyone has any questions about it. It's due on Thursday, remember? I gave you guys a little bit more than a week to work on this one. So are there any questions related to the homework assignment?
Yes.
Okay, go ahead.
Right, so how do we know for sure that that's the result we're looking for? Because
so you have to design a test program to see whether it works or not.
What should be the result of the test? What should receive the processor?
Okay, so you want to design so which instruction are we talking about first?
For example, let's start with the JMPI.
JMPI. Okay, so with the JMPI instruction, you know what it's supposed to do. It is supposed to go to the location that is the second part of the instruction, right? So when you write a program like this, okay, so we'll just go ahead and write a program like this. So you have loop with a colon after that. It means you're defining a label. When you define a label, all you're doing is you're associating a memory location with a symbolic name so that you can refer to the symbolic name so you don't have to keep track of the counting part of the program. Is that okay? All right. So what you want to do is to write a very simple program. You can have some no-ops here just to make sure that you can see that you're going back to the first instruction instead of not executing the jump instruction correctly. Okay, so you can differentiate between those two. And then you can have the second instruction of JMPI loop. So this is a pretty simple program to check that your JMPI instruction is in fact working. Okay. Now there's one more thing that you might want to do. Okay, just in case that your jump instruction does not work correctly, just put a halt after that because we should not be getting to the halt instruction in this case because before you get to the halt instruction, it would have changed the flow of the program back to the no-op instruction. So the execution of this program should be somewhere between the no-op and the jump I instruction.
Okay, so what should we see on the screen while we're writing logic? It should first nothing, then NOP nothing, and then JMPI should jump back to the memory location.
You never really see that, okay? But when you log it, you should see the PC, the program counter, alternating between location 00, 01, and 02. Because PC would actually get the 02 to get the address to go back to. Yep.
Can't you see it in RAM? Like when I tested mine,
yeah,
I would
put
a lot of no-ops, and then I'd make sure that it would go right back to the first spot, because that's where I put it.
Yeah.
And you can see it literally in RAM. It's going, it's going, it's going. So it's like a loop. It just goes back to the beginning, it goes, it goes,
Yep.
it goes.
You can do that too.
So we should jump back in the RAM. The location of the first instruction.
Right, you should, because remember in RAM, it highlights which location is being addressed. You should see the highlight, going from location 00 to 01 to 02 and then back to 00. And also when you track the program counter, you should see the value of the program counter itself going from 00, which is the initial state, to 01, and then to 02, and then back to 00. And that should go in an infinite manner until you stop the simulation. Okay, all right, cool. So any other questions about how to test the JMPI instruction? What about the other ones, the conditional ones? They are a little bit more tricky to test. So let's go ahead and take a look at one of the conditional branch instructions or conditional jump instructions. JOI. Okay, so we'll test the JOI instruction. So I'm going to put a JOI instruction here with a label L1, and we'll define L1 down here somewhere. So right after the JOI instruction, oh, that's joy, right? The joy instruction, we'll have two halt instructions because we want to see whether the branch happened or not. Okay. Because if I stop at the halt instruction right after JOI, that means the branch to L1 did not happen, and that should only happen when the O flag is cleared. If I stop at the halt instruction right after L1, that means the branch happened, which should only happen when the O flag is 1. Does that make any sense? Okay. So now what is left to do, what is left for you guys to do, is to specify a compare instruction or an add instruction. Do something here that can change the overflow flag. Okay, so I'm going to just say CMP_AB, which now pushes the test back to, okay, how should we initialize A and B to force the overflow flag to be a 1, or to force the overflow flag to be clear. That's what you need to do. So that means, earlier than this, you have 2 LDI instructions. One is going to load A with some value here. One is going to load B with a value here. So you just have to decide what values do you want to use to initialize A and B, so that the CMP instruction is guaranteed to either set or clear the overflow flag. Is that okay? But I have forgotten completely what the overflow flag is all about. How do we get this to work? What do you think? Well, you can always go back to the earlier video that we talked about this. So I'm going to give you a quick clue of how to do it. Okay, and we're going to use this box here. Sim generic, and under processor, we'll use the new one. Okay, so we want the overflow flag to be set, so that means we can right click here, show ALU, and you look at the output of the entire thing, because what you need to do is to track your way back. This is the O flag as an output. So you want to track this back and say, okay, so how do we change the overflow flag? Now, for many of the operations, other than an add or subtract, the overflow flag is whatever is in is whatever is out. So the only 2 instructions that can change, or 3 instructions that can change the overflow flag would be the add instruction, the subtract instruction, and also the compare instruction. Those are the only 3 instructions that can change the overflow flag. Okay, so now you look at this, you go like, okay. So based on this part here, how are we going to select whether it's the first one or the second one? Well, they're all selected by this thing, right? This is the selection of which input of the mux becomes the output. Okay, so you need the OP or the ALU operation to be a 000 or a 001 in order for the overflow flag to be meaningful. When the ALU operation is 000, this becomes the chosen input to become the actual overflow output. When the selection is 001, this becomes the actual input to become the actual overflow output. Okay, so now you go back a little bit more and you look at these expressions. So now you just have to figure out what type of input, and what type of output. Well, okay, what is the sign bit of the inputs to the operation, and what is the sign bit of the output of that operation that will make the overflow flag either set or clear? Is that okay? So I'm just going to show you guys up to this part here, because up to this part, then you just have to track down, okay, where is S1 connected to, where is S2 connected to, and what is S out connected to, and how do I change these things relative to the operation that they're going to perform in order to force a 0 to be the output of this particular gate, or to force a 1 to be the output of this particular gate. Is that okay? All right. So that's what you need to do to test the JOI instruction. And let me go back to the document camera. And then the rest of the program is really just using a JOI with a halt instruction, and then another halt instruction at the label L1, so this way you can tell whether it branched or not. Yep.
So again, when we test JOI, we should see in the RAM that it goes like to that specific location of L1.
Mm-hmm.
Or section 1.
And because I use the halt instruction in this case, you can run the simulation at full speed, and when it's all done, the program counter will never change again because the halt instruction is stuck at a certain location.
Is it accurate for all of those that program counter will be changing? Should be changing with every line of the code?
The only instruction that will make the program counter get stuck and not change anymore is the halt instruction. Are we still doing okay so far with this particular homework assignment? How to test it? Okay? Question? No, it's good. It's good. Okay. So now you have the other four flags. Basically using the same way, setting up A and B, and then you just change this O to the other ones. So we have the carry flag, the Z flag. The O flag is already here, the sign flag, and also the L flag, which is a combination of the sign flag and the overflow flag. So you just have to design a slightly different program to test each one to make sure that your implementation of the instruction is correct. But you have to test it in both ways, when it's supposed to branch and when it's not supposed to branch. Because otherwise you can make a mistake and it's always branching, even when it's not supposed to. Is that good or not? Better, okay. Any other questions related to the homework assignment? How do you test it? How do you run the whole thing? Yep.
How do you want us to turn it in?
I want you to turn in a folder, a zip file, which has the entire folder with all the programs that you implement.
Okay, the tests and the C files and everything?
Just the C file. Just the C file is fine. So you need to give me jmpi.c, joi.c, and so on and so forth. Okay, so
you don't want
maybe
the other
6.
ones?
The other ones I don't need because when I test the program, I'm going to use my own makefile and my own other files to combine with your 6 .c files, and then I'll test it in the simulator. Any other questions? Any questions about the tool chain itself, which is a little bit too late to ask, but for those of you who are just waiting until the last minute to get started, are there any questions about the tool chain itself? No questions? Right. Then I'm gonna let this one go for the time being. If you guys have any questions about the homework, just bring it up, during the lecture, and I'll try to address those questions. All right. So the rest of this, assembly programming section talks about, how do you translate a C program into an assembly language program, which is usually the job of the compiler. But in this class, you are it. You are the one who are going to translate a high-level C program into an assembly language program using the toy processor. So we'll be running some code that normally will be run in GDB using code blocks, and it will be running those programs using the toy processor. Is that okay? We did some examples already last time. So this time we'll go ahead and do some more, and we'll see whether we can write some code to do that sort of thing. All right, so I think I can do this one without using the camera. Instead, we'll use mousepad. There we go. Okay. So this time we'll go ahead and say the previous example that we did was to find the maximum of 2 variables and then store the maximum into a third variable, in the third register. So we did that one already. So this time we'll go ahead and try out, well, let's just do something like this. So we'll say I gets 0 as long as I is less than 3. We'll do this inside. And what we're going to do inside is, and then j is 0 as well. J is j plus I gets I plus 1. So we're just adding 0, 1, and 2, and we want the sum to be stored in j. So that's the entire program here. So the program does not really matter. The logic of this program is really simple. I'm just using it as an example of how to translate from C code into assembly code. What do you think? So let me show you which part of the notes I'm referring to. So I'm referring to this part of the notes here. You should read the newer one because I think it's better. But you can also refer to the older one if the newer one is too confusing. The older one is specifying the same thing. So I will open this up a little bit just so that you can see what it looks like, but I'm not going to read out of it. Okay. So going back to the example first. Okay. So how do you do this? How do you do the translation from C code into assembly code? I'm not going to translate this into assembly code right away. Instead, what I'll do is I'm going to quote-unquote flatten this code. This is structured programming. Okay. So I'm going to do exactly the opposite of what you were taught to do throughout all the other programming classes. Because throughout all the programming classes, you were taught how to do structured programming. So I'm going to destructure the program first because assembly language is not structured. So instead of translating this code into assembly right away, I will still maintain this code in C and C++, except it is not going to be structured anymore. So what that means is I want to look at this code, especially this control structure here, and I want to turn this into something that is quote-unquote flat. In other words, I want to turn this into code where the curly braces are no longer needed. How would I do that? Okay, so I keep the stuff before. Okay, I gets 0, J gets 0. We can keep that. That's not a control structure, not a problem. So what do we do with while I is less than 3, which is a control structure? When do we get out of the loop? When I is not less than 3, right? Okay, so we'll go ahead and do that. So we'll just say that while I is not less than 3, I know we can express this as greater than or equal to, but I'm doing everything step by step. And then we say go to and while is a label that you define at the end of this block of code. And what do we do if we are not branching? Maybe we should perform whatever is in the loop, right? Okay, so we say J gets J plus I gets I plus 1, and then what else do we need to do? If I don't do a single thing, this is going to continue to end while all by itself, but the property of a loop is at the end of the loop, you want to go back to the beginning and check the condition again. So how do we do that?
Just set a label.
We set another label. Where do we set the other label? Before the if. Very good. Yeah, we'll call that begin while or while begin because it marks the beginning of the while loop. And then what do we do here? Just a go to, right? The one statement that you are not supposed to use in all of your other classes, we'll use it here. All right, so when you look at this program here, okay, it has a syntax issue because this is supposed to have a semicolon. There we go. And there's another semicolon after the go to. So other than this, have I changed the meaning of the program from the structured version? Okay, we have just destructured the program. But why do you think I want to do this? Why do I want to do this before I try to convert this into assembly code? Because assembly can only do this. Assembly is not structured. Okay?
Yeah, you sort of putting unfolding all the programs, all the lines one by one.
Yep.
So you can translate them one by one.
And I can test it. And I can test it because this is still a C program. I can still test this program using code blocks. I don't have to go to Logisim, I don't have to go to my assembler because this is still valid C code. Do not turn in anything like this in your other programming classes. Okay? Otherwise, Professor Fox or Professor Subsevery or Professor Antos, it's going to give you a really hard time. It's like, why are you using goto and labels and all of these things? But in this class, this is what we actually have to do. Okay? All right, so at this point, I'm going to give you some assumptions to make things easier. I'm going to say register A is I, register B is J, okay? So given that these two particular registers are the variables I and J, can we do some translations at this point? We'll just do it step by step. We'll do the easy ones first. Okay. I think we can do these two first. Okay, these two seem pretty easy to do. So how do we do this? Which instruction should I use? LDI, well, yeah, because we are changing a particular register. If you're changing a register, there are only 3 families of instructions to change the value of a register. LDI is changing a register to a particular constant. You have to be able to spell out the constant at the time of the assembly. LD is going to load the content of a register from a different memory location specified by another register, possibly another register. So that's indirect. Okay, that's not what we're doing here. And then we also have CPR, which is copy register. We are copying a register to another register, and that's not what we're doing here either. So LDI is the correct choice. Okay, so we say LDI A, and then the constant, and then the next one is going to be the same, LDI B and the constant, and we'll just keep this thing around. Begin while as a label definition. That's valid, actual valid, syntax in the assembler. And in this part here, we'll just keep it the same way as it is right now because we'll deal with it later. So we'll just keep this one around. In the loop, I think it's fairly easy to do this part here. So what do we do in the loop? Let me scroll this up a little bit so that people in the back can see it too. Okay, so in the loop, how do we do this part? J gets J plus I. Which instruction can do this? The add instruction. Okay, so how do we specify the order of the registers? No, we don't have I and J. We have registers A and B. BA is correct because the first register is the one that is going to store the sum. So we want J in this case to store the sum, and J is register B. Okay, very good. What about the second one? Second one's a little trickier because we want to add a constant to a variable, to a register. But we cannot do that. There's no add I instruction. So how do we do this?
You load a constant?
Yep, we have to use a register as an intermediate thing. So we have to do LDI, just pick anything other than A or B. In this case, we'll pick C, make it a 1, and then we say add AC, sorry. So we are adding 1 to register A, which is the variable I. What about the go-to in a statement? JMP or JMPI? JMP relies on the register, JMPI does not. JMPI, okay, very good. Because if we don't have JMPI, then we have to load C again with the label and then do the jump. That's the reason why we have a JMPI instruction, to simplify things. So begin while, there we go. And then end while is still a valid syntax here to mark the end of this loop. So it looks like we got most of the things done except for the conditional branch, which is this thing here. Okay. So at this point we have to do a comparison and then do a conditional branch. There's no single instruction in assembly that can do both as one single thing, but we can do it in. So let's look at the pieces that we have. Can someone tell me what kind of instruction are we looking at here? Okay, so I'm going to copy and paste this so that this way we are going to do in-place changes. So can someone tell me what instructions will be involved here in order to implement the equivalent C instruction, C statement? Just give me the instructions, not even the operands. Compare, okay, so it seems like compare is useful. And what else do you think is going to be useful? At least one of those things will be useful. Well, you have to ask me a question first before you can figure that one out. What question are you supposed to ask me? Signed versus unsigned. Very good. Okay, very good. Good question. So we'll just basically say that A and B store. Let's make it unsigned this time. Okay. So given that A and B are unsigned, which conditional branch instruction should I use here? I got $10. Carry, yep. Carry, which is also borrow. Okay. So we have JBI. Okay, JBI because we want the convenience of the JBI instruction. JB would work, or JCI, sorry, here because we don't use B, we just use C in the instruction set. So JCI would work. Okay. We don't know whether we will need an unconditional branch or not because we don't have a JNCI. Okay, if the carry bit is clear, we want a branch. We don't have anything to express that, so we might need an unconditional branch after this one. Okay, but we need at least this much. Okay, so now the question is, how am I doing the compare? I'm comparing to 3. I'm comparing I, which is in register A, to a constant of 3. But I don't have a CMPI instruction, so what do? I have to use register C again as a scratch register. So we have to first set up register C to be the value that we're comparing to, and then we can now compare AC or CA. Which one makes more sense to you? If I want this program to have the fewest instructions, which way of the compare does it make more sense to you? So we are looking for I being greater than or equal to 3, right? If I is greater than or equal to 3, that means 3 is less than I, right? So if I want to express 3 is less than I, which way should I compare? 3 first, right? C, and then A, which is I, second. Okay? So this way I can say if C is less than A, which means 3 is less than I, which means I is greater than 3, then we should branch to end while. But the problem is, this is not the only way that we should be branching, because when I becomes exactly 3, we should branch 2, right? So what else should we be doing here? When we're at this place, it means the JCI did not happen. The 0 flag, very good. So we should also say JZI and while, because we have 2 reasons to get out of this loop. The first one is when I is greater than 3. The second one is when I is 3. And somebody, some smart person, is going to say, but according to this program here, I can only be 3 at the end of the loop. It cannot be greater than 3 at the end of this loop. So why do I want to write this loop in this way? Just because it is exactly a translation from C. Why do you think that might be useful? In other words, in this very specific case, I can basically ignore this instruction. I can comment out this, and the program will still work correctly because variable I will go from 0 to 1, 1 to 2, and then 2 to 3. When it gets to 3, we get out of the loop. So that means, in this particular case, I never gets a chance to be greater than 3. Okay? But why do you think, I might want to kind of just keep that logic in C and also do a JCI in addition to the JZI instruction? Yep.
You're incrementing by more than 1.
If I increment it by more than 1, I can potentially jump over the boundary value. I can also initialize I to be 4 to begin with. Okay, so in that case, I should skip over the entire loop. So I don't want to make this loop dependent on how I is going to be incremented or how I is initialized. Okay, I want to say, okay, this has to work in all the other cases, not looking at how it is initialized, and also not on how dependent on how I is incremented for each iteration. So this would be the correct program, and this is the entire thing. Are there any questions about how we just translated a C program into assembly code? Yep.
Would there be a reason, like if we were to LDI C and then 2, could we remove the JCI as well?
If we
okay, so you say that you have the JCI so that when I is equal to 3, it will. So if we were to set it so that it loads 2 into register C instead of 3, then would it be, since it's all unsigned integers, then could you remove the the JZI as well.
I see.
And reduce the number of operations you're doing.
Yes, you can.
Would that be valid to turn in?
Yep, it'll be
Okay.
fine. Yep. But that can only happen because we're dealing with integers, and
Yes.
you know the next integer has to be that. Yep. All right. Any other questions? Any questions about this particular code? No particular question? Okay. Let's do something a little bit more fun. Let's go take a look at this program, and what we'll do is I'm going to copy and paste a portion of that. Okay, so I will still be going from 0 to, but this time we'll make it go to a larger value. So let's say 330. Okay, and in this loop here, I'm going to replace this, j gets j plus 1, with a conditional statement that will increment j. So I'm going to say if j ampersand, which is bitwise and 1, is 1, or if it is non-zero, only in that case I want to increment j. Okay, what about that? Okay, first of all, what does this program really do? What is it counting? What is j counting? I know I is just going from 0 to 29. J is counting the number of, you got it, odd numbers. J is just counting the number of odd numbers from 0 to 29, which you can figure out just by division, right? But let's just say that we want to do it using this loop here, because the whole idea is how do we translate something like this with a nested control structure inside another one. Is that okay? All right, so let's go ahead and do this one. We already know how to deal with this loop here. Okay, we know how to deal with a while loop, an increment at the end of the while loop. So let's go ahead and do that first. Yep, go ahead.
Sorry, because I'm slightly confused. Do you mean I ampersand 1, or is it meant to be j ampersand?
Oh, that's I ampersand. Sorry. Good catch. Because we have to use I to check whether the number is odd or not, because j is a counter of how many odd numbers have we seen. So good job. This reminds me we should really be using meaningful variable names instead of I and j. We should be using odd counter or something like that, so that we don't make silly mistakes like that. Okay. All right. So let's do the translation here. Okay, easy peasy. We'll still assume that register A has I and register B has J. Okay, so the first part is pretty easy. Just initialize both of those to 0. And we know how to do this comparison already, so we'll just copy that from the previous code. Okay, load C with 30, or load it with 29. Okay, so that we can just use one single comparison to get it done. Okay. Okay, so we'll just use 29 because now we can use one single comparison or one single conditional branch to get it done. So the compare is between the C and the A, which is I. And then we have a JCI. These are still unsigned numbers. And while. And while is somewhere down here. Yeah.
Real quick, once again, how does I ampersand 1 work again? It's you said a bitwise comparison?
It's a bitwise and a bitwise conjunction, which is basically saying that you spell out the content of I using individual bits. You spell out 1 as a constant using individual bits, and then the bits of each location has a conjunction, and you store the and then you look at the result. Okay, so as an example, we'll use the camera because we got it all set up already. Okay, so let's say in this case A has a value of 35, okay? And 35 is in base 10, okay? So the question now is, what is A and 1 going to do? What is the result of that? So the first thing you need to do is to convert the values into binary representation. So 1 has to be represented in binary, 35 has to be represented in binary as well. So we look at 35 in base 10, and then you say, okay, what is it in base 2? So the quick way to do it is to take out the largest power of 2 that is less than or equal to the number that we're dealing with. So in this case, 32. Then we got 3 remaining. 3 is easy. 3 is just 2 plus 1. So now we know it is 2 to the power of 5 plus 2 to the power of 1 plus 2 to the power of 0. So now we can say that, okay, 35 is 1, 1, 0, 0, 0, 1. And then since we're dealing with 8-bit numbers with our architecture, we have to add 2 more zeros to this side. So now we have 8 bits. 1 is easy because 1 is just all zeros and then 1 as the least significant bit. So we have this thing here. And this time we have a bitwise AND operation, which means per column you're doing a conjunction. 1 and 1 is a 1, 1 and 0 is a 0, and basically we know the rest of this thing are all zeros because one of the numbers has all zeros for the rest of it. In other words, the bitwise AND operation is a quick and easy way to isolate individual bits that you want to pay attention to. Is that okay? Okay, all right, cool. Yeah, these are tricks that low-level programming really need to deal with. When you write device drivers, like controlling the USB bus and stuff like that, that's what you need to do because there are individual bits that turn on and turn off a particular feature of the bus. All right, so that's that. And now we go back to this particular program. We also need a label here as begin while, because we need a label to go back to, okay? All right, so we have just taken care of the while loop itself, so we still have the other stuff to take care of in the inside. So I'm gonna do it step by step and just say that, okay, we just took care of the outer control structure, and we'll just leave it the way it is, and then do the inside a little bit later on. Are there any questions about this particular program at this point? I'm missing one more thing too, actually. Since I'm going to handle the loop itself, I should also add a unconditional branch or a jump I instruction here to go back to begin while. Because this is a part of the loop, not a part of the inside of the loop, so I should take care of it now. Other than that, are there any questions?
We're not doing the 0 anymore? The JCI?
The JCI, we are not doing that anymore because the way we compare is now 1 less than the number that we used to deal with. So that's why, as long as A is greater than C, we should get out of the loop because we changed the boundary. Yep.
Should we put the begin while above the load IC so that we can use C?
Oh, right. Yes, we should. Yep. So we should copy and paste this. Good. All right. So now we can focus on the conditional statement inside the loop. So we can now focus on this part here. And what I'll do is I'm going to copy and paste this code. So this way we can look at it before we do the conversion and look at it after the conversion. Okay, so we look at this. And this part is pretty easy. Okay, so we'll do all the easy stuff first. So this is just an add instruction. Once again, it is add B. Oh, this time we have a 1, so we have to do LDIC with 1, and then add BC, because we want to add the 1 to J in this case, and J is in register B. So that will take care of this. And this one is pretty easy to take care of because we just want to add 1 to A in this case. So LDIC1, add AC. That should take care of the increment of I. So now what we are left with is really just taking care of the conditional statement. All right, so we'll make another copy of this code. And this time we'll concentrate on just this part. How do we take care of the conditional statement? What do you think? What kind of instructions do you think is involved here? The AND instruction. We do have a bitwise AND instruction. What else do we need? Do we need a compare? do we need to compare to 0? Because in C, there's an implicit equal 0, or not equal to 0 here. But do we need that in assembly language programming? Yes? No? Okay, let me clarify what I said. In regular C or C++, that it is just implicit that this is what we are looking for. Okay, but a lot of times it's not spelled out, so that we just say, well, I and 1, but implicitly we're saying that this expression is non-zero. So the question is, do we need to compare it to 0? Well, that depends on one thing. It depends on whether the AND operation changes the Z flag or not. Right? Because if the AND instruction is just doing the bitwise AND, storing it back to the first register, but it doesn't touch the Z register, then we have to compare to make sure that the result is or is not a 0. How do we know whether the AND operation changes the Z flag or not? Well, we just need to look at the architecture. We just need to look at the ALU and see whether when we specify an AND operation, is the Z flag going to be affected? That's what we need to check. So we will switch back to LogicSim, and this time we want to track down the Z flag. So we look at Z out here, okay, and we look at Z out, and it is a bitwise. It's a bitwise. Okay, not bitwise, but it's a NOR, multiple input NOR of all the bits of whatever is the result of the ALU. So do you think the AND operation will change the Z flag? Okay, let's take a look at the big picture again. So let's focus on this part here, and I'm going to zoom out. I will zoom out so that you can see the context of this thing here. What is this? That's the output of the ALU. Okay? And how do we determine the Z flag? We look at the output of the ALU regardless of which operation we are performing. So it doesn't matter whether you're adding, subtracting, comparing, bitwise AND, bitwise OR, or bit shifting. All of those operations will affect the Z flag. Okay, so knowing that, getting back to our program here, do I need an extra compare after the bitwise AND? We don't need one. There's no need to do it. Okay, so this becomes your LDI C1 because we need the 1, in one of the registers. And then we just perform an AND operation, and AC, because A is register A is variable I, and here's the C, which is just the constant of 1. And then how do we branch to AND if here? This is the AND if label. I need to go to the AND if label if you have to flip the logic around. Because I AND plus AND1 is where we go to the then branch. So in order to skip the then branch, what is the condition to skip the then branch? If the result of the bitwise AND is 0. Okay, very good. And we just happens to have a JZI instruction just for that, right? Is that making any sense? If the result of the bitwise AND is a 0, then we skip the then branch. Okay, so we take care of that. So now we don't have structure anymore. The structure of the conditional statement is now taken care of by conditional branching. So this is the final version of this code. I'm not going to run this code even though I have already implemented all of the instructions, because when I run the code using all those instructions, you will see the actual slices of the microcode. But if you punch the program into the assembler, assuming your implementation of the JMPI and the JCI instructions, or the JCI instruction are correct, this program will work the way it's supposed to. Are there any questions about this whole process of translating C code or high-level structured code into assembly code? So we have dealt with a loop using a while. We have dealt with a conditional statement without the else but just the then portion. How do we deal with a conditional statement that has both the if and the else? Well, we can always just look this up, okay? So so this is basically just translating into alternative unstructured C code. So in this case, we have a general conditional statement. If C, we perform block 1, else we perform block 2. And if you want to flatten this so that we don't have any structure anymore, this is the equivalent code. It will do exactly the same thing, but it's no longer structured. Does that make sense? Is the highlighted code doing the same thing as the code before that, except it is just unstructured? Is everybody convinced that it is the same logic, or do you guys want to talk about it? Okay. So in order to see whether they're equivalent or not, then you want to look at, okay, when do we get to block 1 in this case? We will execute block 1 if and only if C as a condition is true. Okay, if C is false, we don't want to get to block 1. When do we get to execute block 2? If and only if C is false. If C is true, we don't want to execute block 2. So that's the expected behavior. Then you look at this code here and you go like, okay, when do we execute block 1? Well, we get to execute block 1 if the conditional branch did not happen. When do you think the conditional statement or the conditional branch is not going to happen? When C is true. So now it behaves the same way as the code before. What about block 2? When do we get to block 2? There are two potential ways to get to block 2, because after you are done with block 1, if I don't have the go-to to L2, it will fall through from block 1. And that's why we have an unconditional branch after block 1 to go to L2 so that we can skip around the else branch. So that is really important. What about the other way to get to block 2? Well, the only way to get to block 2 is to jump to label L1. But how do we jump to label L1? This particular go-to has to happen. But when does it happen? It happens if and only if C is false. So now we have the same behavior as the original code. Is that okay? Is everybody convinced that I have just converted the structured version of a if-then-else statement into something that is unstructured, but they behave exactly the same way? Okay, cool. And this is the simplified version where there's no else, or the else is empty, so to speak. So we just translate it into something like this. This is something that we have done already. Are there any questions about this particular slide, which is just translating structured code into unstructured code? No questions? Okay. The next one up talks about another control structure that we have done already. It's a pre-checking loop. While C and C is a condition, do block 1, it is translated into a label L1 to mark the beginning of the entire loop. Then we say if the condition C is false, go to label L2. L2 is labeling the end of the loop. Otherwise, we perform block 1 and then we go back to label L1. Any questions about this part? Okay, we have done this one already. The next one we haven't done because it's a post-checking loop, which is usually a little bit more rare compared to a pre-checking loop. Can anyone think of a situation where you have to use a post-checking loop instead of a pre-checking loop? So you have to use a do, and you have to use a do while instead of a while. Yep.
When the instruction should execute at least once.
Exactly once, or at least once.
At least once.
There are other ways to make it execute at least once, and there are situations where even though you know it has to execute at least once, it still makes more sense to use a pre-checking loop. The only time I use a post-checking loop is when the condition C it only makes sense after block 1 executes, then you have to do a do while. I can give you one example. If you're doing any type of error checking, okay, I'm just going to do this on the side here. Okay, so do ask end user for zip code while zip code is invalid. It makes more sense in this case to use a do while loop than a while loop. Because if you want to do this as a while loop, how are you going to do it? You will do it as while zip code is invalid. Then you ask end user for zip code. It doesn't make sense because what zip code are you validating the first time you get into the loop? It's not something that the end user enters, right? So the only way to get around this one is to have a separate variable to indicate this is the first iteration. Don't ask me about whether the zip code is validated or not. So that's just artificially making this code look even more complicated. So this is the only time that I would use a do while loop, which is a post checking loop, because it checks the condition after the iteration, instead of a pre-checking loop where you ask the question first before you perform the iteration. Okay, so this is just a kind of like on the side to illustrate how rarely do we use a do while loop. Okay, getting back to the notes here, a do while loop it's actually simpler because you have a label to indicate the beginning of the do while loop, then you perform block 1, and then this part here needs no negation because whatever the condition is, you keep the condition to go back to the beginning of the loop. So it's actually a little bit easier and cleaner. But unfortunately, we don't use do while loops too often. Okay, are there any questions about this part? In other words, do we have any questions about translating just typical C code into assembly code when we're dealing with conditional statements, while loops, and do while loops? What about a for loop? What do we do with a for loop? What is a for loop? Okay, let me present a question in a different way so that you guys can answer it. Okay, so if I have a for loop where it has a initialization section, a condition section, a post operation section, and then it has statement here. Okay, so if this is the overall of a structure of a for loop, can I translate this into a while loop?
Yes.
How would you do it as a while loop?
While it meets the condition.
Okay, what about the I and the P and the statement? Where do those things go? Sorry? To start with, we need which part? We need I, okay, it's very good. So we need I to begin with. And then what do we do? We have a while C, okay, and then inside this block here, what do we do? This is the important part. Statement first, very good. Statement and then P, because P is specifying the post operation, which happens at the very end. You have to execute the statement first, and then the post operation happens. Okay, good job. So that's why I don't talk about the for loop, because a for loop is nothing more than a for loop is nothing more than a while loop, except you put components into different places to make it easier to read. What about a switch statement? I don't talk about a switch statement here either, but what can you do with the existing stuff so that you can take care of a switch statement?
It's sort of multiple if.
Yeah, it's sort of a kind of like a daisy chain if, and you're comparing. It's not exactly the same because in a switch statement, the cases can fall through if you don't have a break, which in some way is kind of the stupidest part of C and C++. But I don't want to deal with the switch statements because there are different ways to implement the switch statement, and if you have conditional statements, you can pretty much do the same thing. Okay. All right, very good. So the next question is, what if this C is not simple? What if it's not just whether something is less than something else? What if C has conjunction or disjunction in it? What if it has a disjunction inside a conjunction, inside a negation, inside another conjunction? What do we do about those things? Well, you just read on, right? I mean, that's okay. So section 4 deals with all of those things. What if you have a not? Okay, so we are now focusing on these really simple unstructured conditional branches. So if you have a not, if not C go to L1, you can just transform that into if C go to L2, which skips around the go to L1, and then you have to go to L1, after the conditional branch. Okay, means exactly the same thing. You just use a loop. You have to use 2 more lines of code, but you remove the negation. Is that making any sense? Okay. But most of the time, you don't have to do this. Okay, depending on what is the condition C, most of the time the negation can be taken care of using the Organ's law. Can be done by changing the comparison operators. Okay, so there's usually something else you can do to take care of the negation using Boolean algebra instead of doing it the ugly way, which is this. Is that okay? But if you cannot have any other ways to work, this will work. What about disjunction? In other words, we have C being a Boolean expression, D being a Boolean expression. I just want to take care of the disjunction itself, or the or. What do? Well, this really is just saying if C is true, we go to L1. Okay, let's express that. If C is not true, we'll check whether D is true. If D is true, we also want to go to L1. So this is a fairly easy one to translate. Are we doing okay so far? Okay, so we're dealing with disjunction. Guess what the next one is? We already had negation, conjunction. The next one is going to be what is left? What is the only logical operator that we haven't talked about? We got the not, we got the and, we got the or. The next one is the and, which is conjunction. So conjunction is a little bit trickier because when you have the original statement saying if C and D go to L1, then you have to negate C first, because now you want to say if C is false, well, then we go straight to L2 to continue execution, because this is also basically implementing the short-circuited Boolean evaluation that is specified in the C programming language. Okay. Now, if C is true, then I don't want to go to L1 right away, because I also need D to be true. In other words, if I am here executing the second conditional statement, that means C is already true, but I need to double check to make sure that D is also true before we go to label L1. So that's why we have the second if D go to L1 after the first conditional branch instruction or branch statement. Is that part okay? So does that mean we can handle anything now? Absolutely. Is it going to be pretty? No. And that's why we have compilers. All right, so we have a simple reduction here. So a lot of times, when you have a negation, you can just convert the way you compare, and then you don't have to use the ugly way of doing it. So if you have the negation of x is greater than or equal to y, you can just change the comparison so that you can take care of the negation and still maintain that this is just a simple comparison. Is that making any sense? Okay. Also, you can do this is what we call peephole optimization. You're just looking at certain patterns and go like, hey, I can do this with something that is simpler. Because when you have x is less than y or x is greater than y, all you're really saying is x is different from y, so you can just check for non-inequality in this case. Okay. Any questions about simple reductions? Yep.
Is that how the compiler operates?
Yep, pretty much. Yep, compilers are just systematically breaking down your C code and generate what we call intermediate code in the process. So it doesn't really generate assembly code right away, but it goes through an intermediate code stage, and then the back end is the one that will take a look at the intermediate code and then use it to crank out your actual assembly code. So the answer is yes, you can potentially rewrite the backend of GCC to crank out code for the toy processor. And you can make your all the future homework assignments easy to do by doing that. But reading how the backend of GCC works may take a little bit more than half a semester. Yep.
So the assembly language is different based on the processor you're using, right? Like this is different than the one we use for the Intel processor?
That is correct, but they are usually very close dialects of each other.
So how does the compiler know which processor to like translate the assembly?
That's a good question. Every single compiler is targeting a particular architecture. So I'm not sure about the switch to do that. So you can do a GCC switch architecture. That might show up something.
Does it have to do with like you download the right GCC for your right your right processor? Or
Each one should report what type of architecture it targets. So if you do a -v, okay, let's see if that does anything here. Yeah, so it says, well, this is just the host, and it says the target is the same. So that line tells you that this compiler is compiled. The compiler itself as a program is compiled, so it will run in 64-bit Intel type of architecture, but it also targets the same architecture. Okay? But you can have compilers that have different, between the host and the target. Okay, I can install a quick package to show you that. Okay, so let me do that.
So you can compile like programs for other architectures?
Yes.
Different architectures?
Yep. Aptitude install AVR GCC. That should do it.
Do companies, when they run their software, if they're distributing it, is that how they test it on multiple architectures? Since they probably don't want to like actually switch the processor out?
Say that one more time.
If a company is distributing its software,
Mm-hmm.
they want the software to work on multiple architectures, is that how they compile it for those
Yes.
architectures? And
Yep.
how would they test it if they don't want to use that architecture themselves?
They can usually test the architecture using a simulator. Like in this case, the AVR architecture has a simulator that is already, it integrates with GDB, so it can actually run not only GCC on a cross-platform, but it can also run GDB on a cross-platform, where the host of GDB is just a regular PC, but the target is some other specialized little processor out there. Okay, so I just installed GCC AVR, so I'm going to run GCC AVR-V. Oh, okay, let's look up the names, AVR. Maybe it's just AR? That doesn't make any sense. Maybe AVR. Yeah, AVR GCC is the name of the compiler. The package is GCC AVR. Okay, so when you look at this one and look at the last part of this, where's the target? Do you guys see target somewhere here? Sorry?
It's just AVR.
Second line? Okay, so here's host and target. So the host is still the 64-bit Intel architecture, because that's what my Debian distribution is running on. But you can see the target is AVR, it's a different architecture. So I can still compile C programs, but the output doesn't make any sense to the Intel processor anymore, because it is supposed to be running on an AVR architecture. Any questions about this? What about between Linux and Windows? Can I run GCC in Linux, but the executable that it cranks out runs in Windows? Yep. Yep. So you have your specialized cross compilers. All of these are called cross compilers, where the host is different from the target. So with a cross compiler, you can have the host to do the compiling, but the target, whatever code it cranks out, it can run on a different platform. Can be the same architecture, different operating system, can be an entirely different operating system, a different architecture altogether. The AVR architecture does not even have an operating system. So you're running on bare metal, so to speak, with these particular programs. There are no operating systems, there are no file systems whatsoever. Whatever code you have is whatever code it is going to run. So that's kind of the nice thing of compilers is you can change the back end so you can target anything you want. There are many research architectures, for those of you who are going to move on to graduate school at some point, okay? And if you're in computer engineering and you want to design a new processor with all the cool features and whatnot, how do you test whether your architecture works or not? Well, you got a few choices. You can do everything in opcode, in binary opcode. That doesn't sound very attractive, right? Because you'll be doing the same thing that we're going to be doing, because this is a class where I want you guys to do the assembly code. So what else can you do? Let's say you're designing an architecture and you say, oh, this is a much better hardware multi-threading mechanism than everything that is known up to this point. How do you test your architecture?
You need a compiler for that?
You need a compiler, and on top of that, what else do you need? You need a simulator, right? You need an emulator to emulate the instruction set of this new architecture. Unless you have a lot of money, then you can fab the actual processor, okay? But unless you have a lot of money to fab the processor, you can run it in an FPGA too. You can load the logic sim equivalent logic. Okay, so this is kind of cool, especially for those of you who are going to design processors. So let me go back to here. Yep, this is it. Okay, so there are programs that can take this type of thing and crank out the necessary binary code to use an FPGA or field programmable gate array device, so that this whole thing is now implemented on an actual semiconductor device. So the instructions will execute, quote unquote, at real-time speed. So every clock, it would actually do all the things that you specified in the microcode to do. Okay, so that would be kind of nice because on one hand, it is not too expensive because you're not having a fabrication shop to fabricate the actual processor that you're designing, which is very expensive. But at the same time, it runs a lot faster than a simulator because you're not simulating using software. You're actually using simulator at the gate level to get all these operations happening at the same time. Yep.
Would you need a very powerful system to do something like that?
No, because that's the whole point of an FPGA. Because anything that is happening in parallel here is going to be happening in parallel in the FPGA. Because it's not being simulated, it is actually implemented in gates using these connections that we specify here. So that's a good trade-off between expense versus the performance. But the connection back to what we talked about earlier is that if the team has somebody who knows GCC and can change the back end of GCC to target the new processor, then with some additional work to rewrite the portions of Linux kernel that is architecture dependent, the rest you can just cross-compile. You can cross-compile first of all the tool chain itself. So I would first cross-compile the assembler, GCC the compiler, GDB the debugger, and a few other tools like CP, make, and so on and so forth. Now that you have a basic set of tools, you can now cross-compile Linux itself with some additional code that is dependent on the architecture. Now you have Linux running on a architecture that is not even in silicon yet. And that actually happens a lot. It actually happens a lot when researchers try to figure out, okay, is this a new architecture that is really good for blah, 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 okay? So they actually cross-compile everything. They set up GCC to cross-compile. They get Linux to run on the research architecture, and then they can collect all the benchmarks, all the statistics and whatnot without actually fabbing the processor itself, which I think is really, really cool. So, any questions about what we have just talked about? I went a little bit on the tangent, but I think eventually some of you will actually get to use this stuff. Any questions? No questions? All right, so getting back to the notes, okay, because the notes has a lot more stuff. So where are we? Right here. Okay, so I have a long example after this. Comparisons, general purpose, imitation, a longer example. There we go. So this is a long example, except it's using the I386 instructions, but the first part of this would still be useful. Okay, in the other compiler, in the other assembler, a pound sign is used as instead of // to start a line of comment. So for the most part, this would still be. I should probably do this in the new architecture and rewrite these notes here, because this is actually just targeting the I386 architecture. So when you look at the code like this, how do you start the conversion? We know how to do most of it except for the logical expression part. Okay, so let's do the logical expression part, just that part, because the rest we know how to do already. So we'll go ahead and just do this part, copy and paste. Okay, so now we have just a conditional statement, but it has got a conjunction and a disjunction here. So we want to basically figure out, okay, how do we do this? And we're not going to translate this all the way down to assembly code. We just want to translate this into simple comparison and then the go-to. Okay. What is the first thing that we're going to do about this structured conditional statement?
We're going to break it into separate.
Well, we don't have to break anything yet, okay? But we want to flatten it, right? We want to get rid of the structure. In other words, we want to get rid of the curly braces. So how do we do that? Well, how about we just say not, and then go to and if. Get rid of these, and then have and if defined here. Okay, we need to make this wider. There we go. Would that work? We're looking for the negation of the original condition to branch around the then branch. So we have just preserved the meaning of the conditional statement, but we just got rid of the structure of the code as well. Okay, so we got that done. Okay, so when you look at this code at the highest level, what is the operator that we need to take care of first? The negation is the highest level. Okay. Now, if you want to take care of a negation, there are two ways to do it. You can either use the ugly way, which is to change, to use a control structure way to change it. Then you are basically looking at the negation of this to go to the next line, and then you have an unconditional branch to branch around. Okay, so let's do that part. I'm going to leave it here. I'm just going to copy and paste it so we can compare what we're doing here. So what we'll do is we'll take care of this negation by adding yet another negation. I know we are double negating, but that's okay because we're just following the notes here. Okay, so we'll make this one go to a certain label L1, and L1 is representing a continuation point. But if we don't go to L1, then we are just going to the original label of and if. Okay, so when you look at this code versus this code here, do they have the same meaning? Are they doing the same thing? No? Why not? Okay, fine. We have some pretty good compilers here. Okay, so we have the and if semicolon. There we go. Now are they doing the same thing? It should be. Okay, but what I have just done is to apply one of the transformation rules that we talked about earlier, and specifically we are only applying this one first, okay, and then we apply the negation rule, which is changing something like this to look like this. Are we doing okay so far? So we are just matching what we are doing with the translation. Okay, so now we have this. Then we say, I don't like to see double negation because double negation doesn't do anything. So I would just simplify that first. Okay, so we simplify the double negation by taking out some parentheses like that. And I'm just double checking the nesting of the parentheses. Looks like they're right. Okay, so are we still okay so far? Yes, okay, all right. So now what is the top level operator that I have to get rid of? Is it the AND or is it the OR? Look at the nesting of the parentheses. The OR is the last operation, so we need to take care of that first. Okay, very good. So we'll go ahead and take care of the OR. So we'll say that there are two reasons that we should go to L1. One reason to go to L1 is whatever is to the left-hand side of the OR, which is this part here. And we can do that here and say this is one reason to go to L1. What is the other reason to go to L1? The second part of the disjunction, right? So we say if that, oh, okay, I forgot to copy first. So if y is 1, then we also want to go to L1. So that will take care of the disjunction. So the rest of this code would remain exactly the same. So copy and paste. So are we still doing okay so far? Just comparing this new block of code and comparing that to the previous block of code. Do they do exactly the same thing, even though it looks ugly? Yep. Question? Okay, so they do, okay? Is everybody convinced that this line of code can be replaced by these two lines of code without changing the meaning of the code? Okay, all right. This one is pretty much taken care of because it is already reduced to a single comparison. This one is not. This one has got a conjunction in it. So we need to take care of that conjunction. Okay, so we'll copy and paste this code and say, now we need to take care of this conjunction. Do you remember the template to take care of a conjunction? It says something like this: if not the first condition, go to a branch around the label. So we'll need an L3 as a branch around label here. And then if the second condition, then we go to the original intended label, which is L1 here. So this is the first condition. X is greater than 2 is the first original condition. So that will take the place of this part. This is the second condition, and it's going to take this part here. So now we can remove this original code because now we got the replacement of that. So now the question is this code doing what? Well, actually, I can just limit to this part here. Is this code doing what this code is supposed to do? Okay, all right, so we have one little thing that we have to take care of, which is the negation. All right, so we'll take care of the negation here. So once again, we copy and paste, but this time I don't need to use the ugly control structure way to take care of this problem, because not x is greater than 2 is the same thing as x is less than or equal to 2, so we just have to change the way we compare to take care of that negation. And now we have converted the whole thing, down to a single comparison and a go-to. This is as low level as I can get without getting into the actual instruction set that is architecture dependent. Is that part okay? But why do I want to go through this process if I can just start translating into assembly code from the start? What is the advantage of doing this step by step? You can optimize, okay. What is the another advantage of this approach? Sorry?
You kind of already have some of your products already written for you. Like you don't really need to change too much when you run translate from C to assembly.
Okay. Well, I'm more concerned about, in the process of doing this, did I change the meaning of the code? Did I make a mistake somewhere and I changed the meaning of the code? Okay, so that means what I'm trying to get to is, okay, let me go back to the original code first, which is this statement. We're only focusing on these 3 lines or 4 lines. Okay, so let's just say that I have written a test suite to test this code to make sure it works correctly. Okay, so I set certain conditions about x, y, and z, and I have a particular program to test just whether this code works or not. Is that okay? I can apply that code to any iteration of this conversion process. I can apply it here to make sure that it behaves exactly the same way as before for all the test cases. Then I can apply it to this code. Then I can apply that to this code, this code, this code, and eventually this code here. Because all of these are still valid C code. So whatever I had before that would work on the C program will still work even when it is ugly like this. Because GCC doesn't have any stylistic point to assign to a program. It doesn't complain about bad styles that we are using go-tos a lot. So I can use exactly the same test procedure to make sure that this code has exactly the same meaning as the original code. It makes debugging easier until all the way down to this point. Then we have to drop down to assembly level code. Question? Yep.
You said that the guy that created C did it so he could make Unix, right? Instead of writing it in assembly.
Right. Yep.
So did he write it like this, and then later on they introduced the control structures when structures?
No, he did it exactly the opposite. In other words, he would write everything in assembly code initially, and he recognized and go like, oh, this is a pattern that is happening and happening and happening again. Why don't I just write this is a while, okay? And then have the compiler to automatically put in the unconditional branch back to the beginning, and also do the checking and all the other stuff. So he wrote the compiler to do exactly the opposite, which is.
How do you include these into the C language, like go-to and stuff, and labels in the C language?
Well, go-to has to be in C because a lot of stuff that you do inside the kernel of an operating system cannot be done without a go-to. Because if you want your operating system to be efficient, and a lot of times in order to make it efficient, go-to is a necessary evil to write an operating system. There are certain things you cannot write, there are certain code of an operating system that you cannot write in C at all. Okay? But of the portions that you can, a lot of times go-to is kind of needed in order to make it efficient. Because the price that you pay of using go-to is the code is harder to debug, but the performance gain sometimes is worth it. Good questions? Anything else? So this is what we'll be doing for the rest of this semester. So we'll start with converting code like this. Now, all of these things do not have variables. Okay, we are using registers in place of variables. So at some point, we're going to use variables. And then once you get into variables, do you guys remember what kind of variables do we have? Okay, let me get out of this one. It has to do with subroutines. So when you took cisp310, what type of variables do we utilize in C programming? We have global variables, and then we have local auto variables. Okay, so those two are really different. Okay, in terms of the lifespan when they come into existence and stuff like that. We'll see how far we can go with this toy processor, because to get to those parts like a call frame and stuff like that, it actually is kind of complicated, and I'm not really sure how far we can get with the toy processor. We have all the key instructions. I know that. Okay, it's just from a practical standpoint, how much can we translate in terms of writing a recursive subroutine and stuff like that. We'll see. Okay, we might have to add a few instructions along the way, but you guys know how to add instructions already, so we can add instructions as we need those. Okay. Why are we doing this? Remember the three questions, the how, the what, and the why, okay? How is what we just talked about, okay? Converting some complex C structured code into unstructured code and stuff like that. The what is we are translating code into assembly. We are reversing the process of a compiler. We're doing the same thing as a compiler. We're given high-level code and we're translating into low-level code. And now the question is why? Other than this is a class you have to take in the computer science transfer degree. Yes?
Is it because it helps us understand what we're actually doing, and so it allows
Yes.
us to debug easier later on? Because we'll
Well,
know exactly
yes.
what we're doing.
Yes, because there are certain bugs you can write in the C program where you cannot really figure out why your program behaves like that if you only understand the high-level code. Okay, I'll give you one example. This is depending on the compiler. Okay, depending on the compiler, this code can have really strange effects. I'll just give you one. Void. This is subroutine F. It has a local array. Okay, so we'll make this a char array, and we'll just call it buffer. Has got 10 elements in it. And the question is, what is this program going to do when you do something like that? Or something along that line. Well, first of all, is the compiler smart enough to tell you, hey, there are no element 12 in this array because the last one is buffer 9, not 12 doesn't exist. No, the compiler doesn't care. Okay, so what is this program going to do? Okay, so the Visual Basic approach is good. Because what a Visual Basic program, the equivalent program will do is it will stop the program, generate an exception, and on the screen, it will tell you that on blah, 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 you are trying to access the array out of bound. Okay, and it will give you the line number, you can go to that line and go like, oh, that's stupid. Okay, no problem. C will just do something as if buffer is long enough. But buffer is really not long enough. Buffer only has got 10 characters. You're trying to access the 13th character of buffer. So what is it really accessing? What is it really changing or incrementing by 5 in this case? Well, we cannot answer that question because we don't know how that code is translated into assembly code, right? But what do you have to gain to understand, oh, I know exactly how this code is going to translate into assembly. How is that going to help you?
We'll know what is getting accessed, so we'll know where it goes to.
Yeah.
We will say this is a valid code.
Then you start to understand the symptom of the program, right? When you do something like this, there are certain bugs that you can write into a C program where you can have main colon F, but when it returns to G, subroutine G, that you have never called. But you can explain that once you understand what is underlying this code. Then you say, oh, I know because the register da-da-da on the stack is getting trashed. Okay? So is it a good thing? No, you still want, you don't want to write any code like this. But it's a good thing from the perspective of you look at the symptom of the program. You already immediately have a list of usual suspects. So that can shorten your debug time by a great deal, because a lot of problems like this, when it does happen, if you give the program to someone in cisp310 and just describe the symptom, there's no way they can debug it, because without understanding what is on the stack, why we have certain registers, and how they are used in the context of calling a subroutine, there's no way they can actually explain the behavior of this kind of problem. So the next question is, do these things actually happen? Or is this something that will only happen once in a blue loop? It happens all the time, okay? Now this one is easy to spot because the entire subroutine is set up to illustrate this whole point. But what if this is inside a loop, inside a conditional statement, inside another loop, and this is not a 12, okay. What did I just do? Undo, there we go. What if it's inside a loop and you're using an index instead of a constant? It doesn't quite stand out anymore. right? But if you understand, oh, this kind of symptom is usually because of overrunning a buffer, then you start to look into stuff similar to this. And it really helps to speed up the debug process. Okay? That's one reason. What is the second reason? I know we're running out of time, but since we're already on this topic, why is this important? Why is it important to understand the underlying code of a C program or C++? Because they're really quite similar. Yep.
Write more efficient code because you make more efficient calls.
You can write more efficient code, but for the most part, the optimizer of a compiler can do a better job than a human being. So it used to be true, but not that much anymore. What about from the security standpoint? The importance of understanding the underlying code generated from a C program. What would be the importance of that? But you're studying from the standpoint of computer security.
It leaves less vulnerabilities. It leaves less vulnerabilities.
Well, you would understand why certain things would happen. Okay, you would understand why certain security risks happen. Okay, how to avoid those problems. But what if you want to go on to the aggressive side? What if you want to hack something?
You know how to manipulate.
Yep, you can start to, once you understand the underlying mechanism of a C program, then you can start to question and go like, I wonder if the developers of this particular program make simple mistakes that will open up vulnerabilities of this program. Okay, so how many people want to see that sort of thing in the next class on Thursday? Because I can illustrate it. I can show you an executable, where it's something. It has a password check, except I can find a way to circumvent the password check. Okay, I can do that on Thursday, and I will do it in a legal way, so I don't get taken away and get deported.
It's recorded streaming.
I can do that to my own program. The DMCA does not apply to your own program. So if I'm trying to hack some licensed program with a copy protection mechanism, then it will be a DMCA issue. But if the program is my own, I think it will be fine. So I'll go ahead and illustrate that because I want to give you a reason why this stuff is actually important. Okay. So we'll do that on Thursday, which is also the due date of the homework assignment. So if you're not done with your homework assignment, tonight is a good day to get started on it.